Today I am starting the second chapter of NCRT. The first topic of this chapter is electrostatic potential. This topic you have learned in your 10th class also. I am repeating again. Electrostatic potential at a point in electric field is the amount of work done in bringing unit positive charge from infinity to that point. Suppose there is an electric field due to this charge and P is a point in the electric field of charge Q. Then what will be the value of the electric potential at this point? We have to bring an positive charge from infinity to that point. What is the amount of work done? That amount of work done is known as the electrostatic potential. I have written in mathematical form as charge is brought, unit positive charge is brought from infinity to point P, V may be equal to W infinity to P divided by charge Q. In simplest form we can write it here, V is equal to W upon Q. This is the expression for the electrostatic potential. What is the electrostatic potential? It is the amount of work done in bringing a unit positive charge from infinity to that point in the electric field which is present due to some charge. Then V is equal to W upon Q. It is which type of quantity? It is a scalar quantity because it has only magnitude, no direction. What is SI unit? SI unit you can determine from this formula. Now SI unit of work done is joule, which is represented by capital J. And what is the SI unit of charge? That is your coulomb. It is denoted by capital C. Now on simplifying we get here joule coulomb inverse. It is also known as the volt. Either you say joule coulomb inverse or volt. Both are the SI unit of electrostatic potential or electric potential. You can say this one also. Now the second topic is electric potential difference. The electric potential difference, that means the potential difference between the 2 points. These 2 points are lying in the electric field. Suppose one point is A, another point is B. What is the potential difference between these 2 points? We are carrying a unit positive charge from point A to point B by any path. It may be carried along this path or this path or this path. But the work done in all the 3 cases is the same, as the work done depends only on the initial and the final position. It does not depend on path followed along which the unit charge is carried. It does not depend on the nature of the path. It depends only on the in the position of these 2 points. If the position changes, then the electric potential difference also changes. Now delta V is equal to, you have bring from unit positive charge from point A to point B. That means VB, which is the final position, minus VA, that is equal to WAB divided by Q. It is also a scalar quantity. Same quantity is here, only here is a difference. It is a scalar quantity. SI unit is the same. You can say volt or joule coulomb inverse. Now, since electrostatic potential is a scalar quantity, therefore for the positive charge it is positive, and for the negative charge its value is negative. I am writing here the value V is positive for this type of charge, for positive charge, and V is equal to, V is negative for which types of charge, for negative charge. Now the next topic is electric potential at a point at a point due to a charge, at a point due to a charge, and electric charge, you can say electric charge, or a charge, it is also correct, to an electric charge. Only one charge is present there. Suppose this is your charge, its value is Q, and this is your point O at which the charge is placed. Now this is another point P where the value of electric potential is to be determined. Its distance from O is R. Now to calculate the value of the electric potential, we extend this line in this manner. OPA is produced, and take 2 points. This is your A point, this is your B point. These 2 points are very close to each other such that the distance of the point A from point O, that is equal to x, and the distance between A and B is dx. Again, point charge is placed at point O, and P is a point at a distance R at which the electric potential is to be determined. A and B are the 2 points, close points, such that the distance of A from O is x, and the distance between A and B points is dx. Now what is the value of the electric field at point A due to this charge? So I am writing here electric field at A due to Q. What's its value? You know, E is equal to KQ, E is equal to KQ upon R square. Here R is equal to X, KQ upon X square. And its direction is away from this one, that is along OA, because Q is positive charge, along OA. Now this is the value of electric field. Small work done in bringing unit positive charge from A to B. That means charge is moved in which direction? From A to B. This is the direction of the motion, this one. You can take the direction of dx, that in this direction. Now the electric field is in direction. The value of dx is in this direction, and the value of the electric field is in direction. The angle between these two vectors is equal to 180 degree. Now dw, work done, that is equal to F dot dx. You can see here F dot dx, and you know the relation between F and electric field. F is equal to Q naught into E. Here the charge is unit positive charge, that means F becomes equal to E, since the charge is unit positive charge. So in place of F we can write here E directly. Now A dot B is equal to AB cos theta, that means E dx cos, what is the angle of theta? That is equal to 180 degree. This is here 180 degree. And what is the value of cos 180? That means cos 180, you can write it here, cos 90 plus 90. It comes in the second quadrant, and in the second quadrant only sine and cosec are positive, all are negative, and sine is converted into cos, cos is converted into sine. That means this becomes equal to minus sine 90 degree. That means that is equal to minus 1. We have not to calculate in the examination. Put the value of sine 180 directly. It becomes equal to E dx minus 1. That means you can say dw becomes equal to minus E dx. This expression is very important and can be placed within the square. Now you can substitute the value of E from this expression. Then you will get here, again comparing these two equations, we can write it directly. That means you can write here, this implies that dW is equal to minus kq upon x square dx. Now we have to determine the total work done. As per the definition of the potential, the unit positive charge is brought from infinity to this point. Then what are the limits of the integration? That means initial position means x is equal to infinity and the final position means x is equal to r. Now total work done in bringing unit positive charge from x is equal to infinity to x is equal to r. The initial position is infinity as per the definition of the electric potential, and the final position is r, at which the electric potential is to be determined. Then what is its value? We have to integrate the above expression within these two limits. Now W becomes equal to W minus, sign comes outside the integration, Q also constant comes outside the integration. Here variable is x, therefore x square remains inside the integration. Minus Q comes out and K also comes outside the integration, Q also comes outside the integration, x square remains inside the integration. This is equal to, limit is here from infinity to r, 1 upon x square dx. Now in the 11th class we have learnt some general formula of the integration. You know, x raised to the power n dx. This value becomes equal to x raised to the power n plus 1 upon n plus 1. Now you can write it here also, minus kq, when it comes in upward direction it becomes equal to x raised to the power minus 2 and dx. Now this is of the same form as of this one. This can be right here kq, you can write here x raised to the power minus 2, here plus 1 divided by minus 2 plus 1, and within the sign of integration, that is means infinity to r. Now minus 2 plus 1, that is becomes equal to minus 1. You can write it here, minus kq x raised to the power minus 1 upon minus 1. Minus 1 comes outside the integration and this is equal to x raised to the power minus 1. You can write it here 1 upon x, and this is the limit infinity to r. Minus minus becomes plus, that means kq. Now in place of x we have to write 1 up r and then minus sign, and in place of x we have to write infinitive, that means 1 upon infinity. And you know the value of 1 upon infinitive, it is always equal to 0. That means W comes out to be kq upon r as 1 upon infinitive is equal to 0. This terms becomes equal to 0. W is equal to kq upon r. This is the amount of work done in bringing unit positive charge from infinity to that point in the electric field. That means this is the value of the electric potential. That means V is equal to W. This implies that V is equal to kq upon r. And what is the value of K? K is equal to, you know it, 1 upon 4 pi epsilon naught q upon r. This is the expression for the electric potential due to a point charge, due to a single charge. Now if we draw the graph between V and R, E and R, you will get, this graph comes 2 marks in the board examination on the same graph paper. we have to draw this graph. Graph paper means on the copy, ordinary copy, which board copy. This is your x-axis and this is your y-axis. Here we have taken R sign. Here electric field and electric potential both are taken along the y-axis. Now you know V is equal to KQ upon R. This implies that V is inversely proportional to R. And what is about E? E is equal to KQ, same charge, R square. This implies that E is inversely proportional to R square. Here V is inversely proportional to R, whereas here E is inversely proportional to R square. On the same graph paper we can draw it. This is your electric field, suppose. This is your electric field, which is R square proportional to, and this is your electric potential, which is represented by the dotted line. This is the difference between these two. This is your electric potential, this is your electric potential, this is the electric field. You two have to represent the either this dotted line or this dotted line, so that we can differentiate between electric potential and the electric field. Why this graph comes in this manner? Due to this region. This is the region due to which graph comes in such a manner. Now the next topic is electric potential. Electric potential at a point due to group of point charge. A large number of charges are present and we have to determine the value of the electric potential at that point due to group of charges. How can you determine here? You must